Welcome to my contribution on digital transformation of surface engineering. First of all, I would like to thank the organizers for inviting me and giving me the opportunity to present our results. Co-authors of this contribution are Holger Gerdes and Falco Oldenburg, who contribute with respect to digitalization and data science, Thomas Melzig, who's involved in simulation and modeling, Andreas Pflug, who's head of the group of Simulation and Digital Services, Michael Vergöhl, head of the department, Optical Systems and Applications, and Christoph Hermann, the director of Fraunhofer IST of our institute. I will switch off the camera since there are some pictures also in the lower right corner to just give you the full side of the presentation. The outline of the presentation: after a forced introduction and motivation, we will switch to digitalization and data management, addressing some of the situations, giving some examples. Then I want to talk about surface engineering for sustainability and the contribution of thin films for different aspects of sustainability. And the last part of the contribution will be about the digital twin of a vacuum coating process that is motivated for coating a 3D shaped lenses. And then I will summarize and conclude this contribution. So what is the situation today we are faced? We have moved from the industry 1.0, 2.0, 3.0 to industry 4.0 in that case. So that is from mechanization using steam power to mass production using an assembly line and electrical energy over automation with computers and electronics in today's world where we have cyber physical systems, the Internet of Things, networks. And Industry 4.0 is the current trend in manufacturing technology. Sometimes you even find Industry 5.0 or 5.0 as some of the names coming up. We have the current trend, it's based on smart factory concepts, and smart factory itself is modular cyber physical systems that monitor and control the manufacturing processes. So it's a series of different cyber physical systems put together for the factory. Digitalization addresses the point that manufacturing is digitalized and carried out on demand and often to near net shape to produce as close as possible and to avoid as many later processing steps as possible that would be required. How can we improve our manufacturing? How can we move to a lean manufacturing? There's a reference. I would like to just quickly go through the 7 wastes of manufacturing or lean manufacturing. The waste is overproduction. We have too much. We produce too much. We have to keep stock of all the material. We have huge warehouses that we need. There's a lot of transportation and movement between different places. We need people that access or process material or information. We might have to wait on previous steps, on parts. We have to deal with defect. We have to sort out errors and mistakes and correct the problem, reduce and optimize. And we have to deal with overprocessing. And all those aspects we can minimize, and then we can increase the added value and maximize the value. So removing waste adds value and improves the productivity. And what we want to have is we want to bridge the digital gap. We want to draw benefits from the digitalization. We want to better utilize the assets that we have. We want to reduce dependency on tactic knowledge in manufacturing, in production. We want to reduce time and costs that are linked to product verification. We want to have a on-site, in-situ quality control and verification. We want to improve or visualize all the business metrics like yield, cost, delivery quality, equipment effectiveness, and so on. We want to enable and improve design for manufacturing and want to be able and flexible to act on new business opportunities. We want to build on a framework for developing a resilient business. We were talking about digital transformation. So the previous steps before digital transformation is the digitization Digitization is the conversion of the analog assets and processes to digital to keep up with the technological changes. So that was already last century where we had the transition from analog to digital. Then we have digitalization, we have automated processes, and we streamline the process, we automate the processes. And digitalization is the converting business processes using digital technologies to increase the business efficiency and revenue. So we improve processes by digital technologies. And digital transformation is more addressing the mindset, bringing in the human factor, involving the human in the situation. A digital transformation is an approach to problem solving through technology. It's more about the people and their mindset than it is about the technology. It's using latest technology, emerging technologies to build business. Collecting all the data, addressing aspects on digitalization and data management. If we have a product, if we have process or production line, we have our part, we have material that's moving within the plant between different steps. We have, for example, a pre-treatment that's creating a report. The next step would be a modification or a coding of our part, and then we do some quality analysis and we characterize the outcome. We have different reporting, and the human is moving between the different steps and brings the information together and is correlating the parameters. But what we want to have is we want to follow the material flow and collect the data. So within the different steps, different kind of information is generated in different file format. Maybe we have structured data which is coming from the PLC, which are automatically generated files by the different systems themselves or relational databases. We have unstructured data like communication by mails, protocols with text editors, spreadsheets, and so on. And the goal is to get all the information from the different processing steps, from the different sources into our database, to use some logging for the different processes, to use the information that we can access and bring it in the database to use, for example, AI, artificial intelligence, to feedback, to control the processes. We can visualize the results, we can analyze the results, and we can put it into simulation and modeling. If we have a cyber-physical system, we have a system that is generating data, and the data is accessible by an open protocol server. We can use different data logger that are fully flexible to store every data point in time steps as we prefer or as we need them. We can use the different databases to access that. So we have infrastructure or construction of a middleware that is used to collect the data, to put it in the database, that we can visualize the data within the dashboard. We can use it for optimization of our tools, of our production, and we can feed the data into a digital twin using simple models or detailed models, using artificial intelligence to create some output like process properties and film properties and connect the physical world with the digital world. And we want to rely on open source software to be flexible and not connected to a specific supplier. As an example, we want to look at an industrial water-based cleaning system where we have the physical world with the cleaning system and we have the cyber world with a digital model of our cleaning line where we can create model-based prediction on the input parameters, on the feedback we have. We can have a live monitoring and correlate it and use it for the active control to have an automated adaptation, for example, of dosing of special ingredients, cleaning agents, and controlling the process parameters. This is a picture of our cleaning line with different process steps that we have. And what we want to have is we want to develop a customer-specific cleaning process, including drying and corrosion protection. It's important to select and test the chemical cleaning system tailored to the specific material we are dealing with, and we want to supervise, we want to control the boss quality and the cleaning results, and we get information, we can prepare substance and energy balances and also get information about our CO2 footprint. In our system, it's a fully automated data acquisition with approximately 300 sensor points, and the measurement interval depends on the individual sensor, on the individual situation, and will be collected every second, every minute, or every hour as it is relevant or desired. This gives an overview of the dashboard on all the different stations in the system that we can monitor. We can see trends, we can see the development, and you get just a broad picture of your process. And then you can zoom in. For example, if we want to look at the energy consumption, we want to determine the energy consumption of our system. We can get a readout of the current consumption over the day of the processes, whether we are running the process. We can see if there's a high current demand, if it's dropping down, and we can determine the CO2 footprint of the product by the information that we gain. Here you can see the temperature change when we enter with a massive part which is warm into a bath. We can see when we are entering the bath that we increase the temperature. There's a jump in the temperature because the part is heating up the bath to some extent, exchanging the temperature between the bath, the surrounding environment, and the part itself. And also it's influencing the conductivity of our cleaning solution itself. And that's quite sensitive because this gives information, the cleaning agents, whether we have to recalibrate or to add some cleaning agents, but it's also depending on the temperature. So you can see directly the interaction between the baths in the process, and we get an in situ visualization of the influence of the substrate temperature of the bath on the bath temperature. We get quality control sheets on the long term. Here you can see an example over a period of 2 months, and you can see the energy consumption, determining the energy consumption. We can see the bath temperature. We have corridor where we want to keep in. We have a lower and an upper warning limit, and we have a control limit of our process, and we want to keep our process within a given boundary. And we have access to real-time quality control charts in that situation. If you don't have new equipment that's existing and has already all the data, you also can retrofit existing equipment. So like we did with a coding system, vacuum coding system that's shown here, we added some sensors, and we want to upgrade the system to get access to machine information, process information, and to get correlations between the process parameters and what's happening with the product, with the coding itself. So we want to correlate the production parameters with the coding properties finally. One example here is for a given power. So we are operating in constant power. You can see on the plateau levels, there's a constant power set, increased in different steps, and the power was kept constant, and we are monitoring current and voltage. And what we can see are some of the overshoots here. This is some arcing of the process, some undesired events that we can see. We can monitor, we can trace back, and also correlate if there is some failure, if there is some issues in the coding. Furthermore, you can see some oscillations on top of that, which is correlated to substrate movement, which is correlated since our coding source is a cylindrical cathode, is a tube that is rotating, and if there is uneven rotation, you see some deviation in current and voltage signal. All those information you get, and you can collect and improve your process with that. A third example would be retrofitting older equipment. Quite often you have, for example, some analytical tools. In our case, we had vibrating sample magnetometer to characterize magnetic properties of coatings, and we don't have access with that system to our intranet due to some security issues, and we can't handle the data directly. We are using a reverse proxy server that provides like a web page for upload the data. So we have spreadsheet, we can create some interface where we can upload the data, and this looks like the follows. We have an isolated system, our measurement tool with maybe an old program, an old computer, and then we have a small single board computer with an operating system that's always up to date and is used as a reverse proxy server. And by that single board computer, we can upload the data in our database in the intranet without running in conflict with any security protocols in our institute or in our production environment. From our analytical system now, we get our measurement data, we get it by our remote proxy, and we put it into our intranet, import the data in the database, and then we can convert it and read out the values, the physical values and the properties of our system. We also can use other tools like Excel or other sheets and to have some masks to get access to the database to read out specific data of our processes and our production, and then can learn from this, correlate the data, put it into some algorithms and further improve and feedback the system. And with artificial intelligence, we can run into a self-learning or improved situation, for example. How can surface engineering contribute to sustainability? Coatings can significantly contribute to sustainability and efficiency. For example, addressing resource efficiency. We can conserve scarce material since we are only applying the material on the surface or the part of the surface of our product where it is really needed rather than costly bulk material. We can address issues like energy efficiency. We can reduce energy, for example, in transportation by using low friction coatings, by reduction of friction, in aviation by erosion protection or thermal barrier coatings in gas turbines. And we can become and be environmental friendly. We reduce toxic effluents, try to avoid critical chemicals and expensive disposal. In surface engineering or in vacuum processes, we are using thin film functional coatings only where it's needed. So we have only a small amount, a significantly reduced amount of material we're using. We try to substitute scarce or precious material. We have just thin films instead of massive parts, or substituting gold contacts, massive copper, and we go to a green processing. Examples are for energy conservation, of course, tribological coatings, reduction of friction loss in engines, in machines, on any parts in contact where you have wear and friction, using hard coatings like DLC, nitrides or carbides. In architectural glazing, low E windows, switchable glazings, like shown here, that's the Sky Bridge at Fraunhofer IST, where we have electrochromic windows. Here you see the switched windows for keeping the inside cooler, and here you have the bleach stage where you just have a transmission, a normal transmission like with the normal glass. We can use thin films for energy harvesting, to power sensors, to charge or even avoid batteries that are used, address tools in the Internet of Things, use it for assistance, for example, in an aging society, to get additional information and support by that. We can generate or convert energy, like in photovoltaics with solar cells, in fuel cells, electrolyzers, having bipolar plates, coating of bipolar plates, porous transport layers, tribological or protective coatings, for example, for wind or wave power, in gas turbines, whether in stationary or mobile turbines, like erosion protection or thermal barriers. We can store or utilize energy in thin film batteries to have new materials or less material use than in thick film approaches, to use separation membranes, for example, for the extraction of highly pure, high purity hydrogen from mixed gases, or in hydrogen fuel cells, coatings for proton exchange membranes or solid oxide fuel cells. And with that, I would like to combine aspects on the surface engineering and the digital data and the modeling in an example of a digital twin of a vacuum coating process. There are several simulation or modeling tools available in thin film technology that we can see. We have different kinds of material models, process models, and they are quite complex. So they consume a lot of time. Here somewhere is given the real-time limit. If we want to have a digital twin, we need real-time models. We need something that's acting in real time and giving the input. We have cyber-physical systems that are connected with the digital twin. We have the real device, sensors, actuators. We have factory models that are connected. We have the life cycle assessment, and we have optimization in our process. Classification of models and simulation approaches that we have, like mentioned before. If it's model drivenness, we have a high amount of CPU hours. We need a lot of calculation time. And here we want to have a data drivenness in the system itself. So looking on the material and process models. So for example, having the material models really on the atomic scale, having ab initio calculation, having the physical constants, having molecular dynamics, classical potentials that using quantum mechanics. We have kinetic Monte Carlo, where we have activation energies that can be obtained by the molecular dynamics. Then we come to process models, where we have several particles, superparticles, more collection of particles. We have particle in cell Monte Carlo, where we can already consider reactor geometry, electrical boundary conditions, cross-section, the different species or the operation conditions like pressure. We have direct simulation Monte Carlo, where we, for example, in a sputtering process, get information on the target erosion profile. And then we have computational fluid dynamics, where we can see temperature-dependent diffusion, viscosity turbulence coefficients, and we can derive this from kinetic collision parameters. If we go to the factory models or life cycle models, we have the dynamic systems using pressure or temperature as an internal parameter. We have discrete events like the process time or the mean time between failure. We have agent-based methods, that's individual process time, mean time between failure, the product quality, and so on. And in the life cycle models, we can address with system dynamics, stocks, flows, internal feedback loops, time delays, adoption rates. We have an economic input-output life cycle assessment, where we have an interrelationship among sectors of an economic system. And we have material flow analysis, where we can get energy flows or material flows and emissions. And we want to put this together. One example is given here. We have a very small 3D optical lens, and this shall be coated with a bandpass filter. The problem is that if you are not looking perpendicular, if the angle of incidence of where you're looking is maybe just 16 degrees, you will occur a shift in your filter system, in your bandpass filter, and you want to have a very narrow bandpass. Even by the natural situation, depending where you are due to the curvature, you get a deposition profile, you get a deviation from the 100% rate due to the curvature of the system. And this will result in a shift of your peak, and that might be quite significant if you have 95% thickness. So here, and that's not even the outer radius, instead of a maximum of the bandpass filter of 670 nanometer, your maximum will shift to 630 nanometers. And you want to compensate this and take account for this in a real-time model. How can we do this? If we recalculate with the thickness, we can see there's a significantly smaller shift due to the geometry. There will be a shift, but it can be significantly reduced by applying the model and by having automated corrected process. We want to be in the real-time mode, so we need something fast. And in our case, we decided to go on the ray tracing. We have a ray tracing for a 3D deposition profile. Here we have our turntable. We have big disk, a big table that is rotating, and the lens is mounted on the lower side of the turntable, and we have some sputtering sources indicated here with the circles, and the areas here indicate where the material is distributed. So we will have some material coming from down here up in that area. There is some masking to more homogenize the coating distribution in the situation, and the table is turning all the time. And we provide selected angular histograms in that case for each position and can trace it back. And by that we can calculate the situation for the coating thickness. In detail, it's a lot of different contributions that we see. We use plasma simulation, which we have seen is time consuming, is not real time. So all the processes here on that line are not in real time available, but we use plasma simulation. We get electron density contributions in our system. From that and from the calculations, we get the ion flux on the target. We get the material of our argon, which is releasing the target material and providing the spotted flux. We get some averaged profiles where we see this is the erosion, and that gives us the material that's transported toward the square here, which is our substrate or the area of the substrate. And then we feed all that in the ray tracing approach, coming to a real-time situation where we now can see, okay, we are moving in this situation, we have our lens, and we can calculate the situation for the coating. So if we look at the situation, we have our two sources, we have some masks to provide the uniformity we want to need with a special design. We have a monitor substrate giving us the reference and having the actual lens. And this is the situation that we have with the design, and that is the calculation and fitting of the real-time monitoring of the process, where we can code in the system to maintain the bandpass filter we want to have, and then end up with a coated lens as designed. So here you can see the system. We called it the EOS, Enhanced Optical Sputtering System, which is the coding system here. Here you can see the turntable inside the physical world. That's the cyber world with the monitoring, and it's connected by the data acquisition and the feedback loop. And the control system offers a stable and easy to use process without complex process control. It combines the advantage of the ion beam sputtering with a stability and high quality, and evaporation, where you have a high deposition rate, and you can go to larger substrate sizes. It's built for continued change of designs to meet the customer demands, and it offers inherent long-term stability, produces clean and reproducible coatings, and that's a commercial system available now on the market. Coming to the conclusion, we are living in the situation in the time of Industry 4.0 and digital transformation today. We have to learn to, sometimes we already have learned how to handle the big data, so we can digitalize all parts of our production equipment and use that in surface engineering. There are several aspects and solutions for enhancing sustainability. And we can create, by combining digitalization, combining the real world with the physical world to a digital twin, a system which is in real time, fully automated and sustainable for production. Thank you for your attention, and I'm looking forward for any questions.